Good morning. I hope that everybody is doing great this morning. All right, we are going to continue talking about conservation of energy. All right, so in our notes with conservation of energy, we talked about how a pendulum exhibits conservation of energy, but in addition to pendulums, we do have roller coasters. All right, so roller coasters do also exhibit conservation of mechanical energy. All right, so if we're designing a roller coaster in which a car will be pulled to the top of a hill of some height h, and then starting from a momentary rest will be released to roll freely down the hill and toward the peak of the next hill, which is 1.1 times as high as that first height, will your design be successful? So what it is saying is, if this is the height or this is the hill that you start on, you go down that hill and then go up to another hill that's slightly taller, will that work? And the answer is no. All right, you will not have enough energy to get you that high. All right, so theoretically, if this is the height that you start at, then you will only be able to make it to that same height on the very next hill. All right, and that's assuming that we have not lost any work or any energy due to friction or air resistance. All right, now on this, all right, this is kind of like the video of the skier the other day. So I do want you to go and to watch this. But what you would see is that as this cart is at the top of that hill, all right, all of that energy is GPE. That's what you see right here. Well, as it goes down, you would see some of that PE, that GPE, turn into kinetic. All right, and so you would have this whole transformation of all of this the entire time. But what I want you to notice is that the total mechanical energy would stay the exact same. All right, so for this one, this is kind of breaking it up. So at point A, all of the energy is that GPE. At point B right here, you see that you do have some potential energy, all right, because it is at some height, but it is still moving. So you have a little bit of kinetic energy. But once again, that total mechanical energy is the same. At point C, notice that point C is a little bit lower than point B. So there's not going to be as much gravitational potential energy, so you would have more kinetic. But once again, that total mechanical is going to be the same. All right, and then at point D, this is at the zero level. All right, so that is at the zero level. So that tells us that all of our energy is kinetic energy and none is GPE because it's at that zero level. But hey, look at that total mechanical energy. All right, and then point E is just a little bit above that zero level. So you do have a little bit of gravitational potential. All right, while most of it is still kinetic. But once again, that total mechanical energy does stay the same. And so we have to remember with both of these, we know that our mechanical energy, which is conserved throughout this entire thing, is equal to our kinetic energy plus our potential energy. All right, so this is our practice problem. All right, so this is a pretty big deal. All right, so if we know that all of our energy right here is potential energy, and we have a grand total of 450,000 joules of potential energy, again, we know that mechanical energy is potential plus kinetic. We know that the entire time, throughout this entire thing, the mechanical energy will remain 450,000 joules. All right, so V, or our velocity at this point, is super easy. We were told that we have no kinetic energy, so that means that we have no velocity. All right, to find our height, we know that GPE is equal to mgh. Solving for h, we divide by mg. Our mass, I told you right here, is 1,000 kilograms. So at this point, we have 450,000 divided by 1,000 times 9.81. As you put this into your calculator, you have to remember to put parentheses around your two denominators. All right, so we do the math, we divide, and we should get a height of 45.9. I'm going to do this over here. 45.9 meters. All right, so that is at a height of 45.9 meters. All right, so it goes down the hill. We know that all of that has been turned into kinetic energy down here. And then we're going to keep going. We're going over the loop. All right, that loop, we have both kinetic and potential. So the first thing that we can solve for is that kinetic energy. Well, again, we know that our mechanical energy is equal to our kinetic plus our potential. All right, we know our total mechanical is 450,000, which means that we are going to subtract that 200,000 of potential energy to get our kinetic. All right, so that's going to give us a kinetic energy of 250,000 joules. Holy moly, that's a lot. All right, to find H, which is D right here. All right, we're going to use this same setup, but instead of 450,000, we're going to use 200,000. All right, so 200,000 divided by 1,000 times 9.81 does give us a height of 20.4 meters. All right, so that height is 20.4 meters. All right, to find velocity, we are going to use our kinetic energy equation. All right, KE is equal to 1/2 mv squared. All right, we have rearranged this equation so many times. So we know that velocity is equal to the square root of 2 times the kinetic energy divided by the mass. All right, so for this one, that's going to be 2 times 250,000 divided by the mass of 1,000. So here we get a velocity of, what do we get? 22.4 meters per second. So we get 22.4 meters per second. All right, so now at our last point, hopefully we notice that our last point is at ground level. So if we are at our 0 level, that means that our potential energy is 0, which means that entire mechanical energy is going to be kinetic energy. So our kinetic energy is 450,000 joules. All right, the last thing that we have to solve for is our velocity down here. So we know that our kinetic energy is equal to 1/2 mv squared. Solving for velocity, we know that that's going to be 2 times our kinetic energy over our mass. So I'm going to pull this down here. That's going to be the square root of 2 times 450,000 divided by 1,000. For H, we do get a velocity of 30 meters per second. 30 meters per second. All right, we're not really worried about our acceleration right here. All right, we're just going to assume that our acceleration is negative 9.81 meters per second squared. We're not going to worry about this angle here. All right, so again, this is showing you what kind of changes happen on a roller coaster. So right here at its highest point, all of that energy is GPE. All right, so it slows down or it stops. It comes to a stop for that split second to kind of heighten your anxiety level before it starts to fall. All right, so we know that as it starts to fall, that GPE GPE is turning into kinetic energy all the way down. All right, that X should be right here, sorry. All right, and this is our zero level. All right, that's our ground level or our reference level. All right, so at point X, all of that GPE has been turned into kinetic energy. All right, so as it climbs back up, some of that kinetic energy is turning into GPE again. And at Y, it has both kinetic and GPE. All right, so it keeps turning back into kinetic. All right, and then here at Z, it's mostly going to be kinetic, but because it is not at that zero level, it will have a little bit of GPE left in it. All right, now I am going to attach this video. This link doesn't work anymore. All right, but this is kind of disturbing, but also kind of interesting. This is a euthanasia coaster. This is purely theoretical. It was created by a Lithuanian scientist. It's a little bit disturbing. All right, but he said that this is going to be used whenever the earth is overpopulated, which is kind of scary too. All right, so this is used to kill people, but they will die happy. All right, so what you see here is that passengers would be taken up to a height of 1,600 feet, like holy moly. And then as they dive down, they are going to hit a max speed right here of about 220 miles per hour. All right, and then as they go through 7 different inversions, they will hit about 10 Gs and maintain that. All right, so on our video that we're going to watch about the physics of roller coasters, you will see that decreases the amount of blood supply to the brain, which does put you in a state of euphoria, but it is super dangerous whenever you maintain that for more than like a split second. All right, so his reasoning behind it is that people will die, but they will die happy. All right, like I said, it's kind of creepy, but it's also kind of cool, but whenever you think about the physics behind it. All right, so don't worry about this slide. All right, we will continue talking about physics of roller coasters and conservation of energy later. All right, but as always, if you have any questions, just let me know.